already know these things. For you, it's going to be a little bit harder. So I will make some recommendations from the beginning about what I think you can do to help with that. We're going to start with this definition right here, something that should already be a part of your knowledge base, but may or may not be. If you don't remember from last year, or you didn't have a course in physics last year, then work is about force and displacement. Technically, that's what it's about. But what it really is about how you transfer energy from one thing to another. Force is the middle ground. Force is the method by which energy is transferred from one thing to another. It's important that you realize that in Newton's 3 laws, the third one indicates that for every force, there's an equal and opposite reactive force. So if I push on something, that thing pushes back on me. Now, if I push on an object with the goal being of changing that object's energy, then by Newton's third law, whatever energy I give to the object came from me. So when we talk about work, if something's energy was increased by a process, somewhere else, something's energy was decreased by that same process. That's just a result of Newton's third law, that for every force, there's an equal but opposite reactive force. So when we talk about work, we are talking about the application of force. So defining work, technically, I should explain it like this, because this is the technical definition of work. And again, all of you who have not had a calculus version of physics, this looks more complicated than it probably needs to be. But this is the equation that tells you how much work is done. Don't get too attached. There's a lot of things here that need to be adjusted. There's a lot of other ways to calculate work as well. But if we're talking about remember, we try to start everything from a first principle. This isn't a law. This isn't really a principle. This is a definition. This is how we define the transfer of energy. So you'll notice there's a dot product in here, which means work itself is a scalar. It can be positive and it can be negative. Positive work increases an object's energy, while negative work decreases an object's energy. It's that straightforward. Now, when we talk about energy, I'm afraid that's kind of it's a difficult term to define. It gets kind of circular logic really quickly. Like if I say something has energy, what does that say about the object? Can somebody give me something that you learned from last year? Really? Nobody remembers anything from last year when it comes to energy? That's disappointing. Go ahead. So we would have used a different work besides change, but that's a good start. So like I said, it was kind of circular reasoning. So we used to say if something had energy, it had the capacity to do work. So that's what I mean by circular. So by doing work on something, we change its energy. Now that it has energy, that thing can go out and do work on something else. It sounds circular, but remember, the exchange of energy is something that occurs in the universe. When we're giving things energy, it's usually for them to go use that energy to do something else. The thing is, it's how the energy is being used. So I might have an electrical system that's designed to change energy from electrical to thermal. I'm going to heat something up, right? I just did just a minute ago. I use electrical energy to make hot water. I wanted to take the electrical energy that I had, have it do work on the particles in the water to change their thermal state, increase the amount of energy in the system. Once the water was hot enough, it could brew my coffee. But we were moving the energy through the system. So we used electrical energy to do work on the water particles, probably ultimately through some heating element or something like that. The heating element got hot. It changed its thermal state. So when we talk about the transfer of energy, it's all can be boiled down to work. There are lots of different ways to calculate work. This is just one of them. Now, for those of you who don't understand the right side, let's step through what the right side says so that we get a clear understanding of what's being said here. And then we'll talk about some maybe simpler ways to write our definition for work. First, we have to come back to the fact that this is a force. individual forces can do work. I want to bring that up because this is different than saying net work. Who remembers what the word net stands for? Total or sum. That's right. So I'm just talking about work being done by an individual force right here. I could just as easily say net work, which would equal all the same things I've just written, but with just that pesky little summation character in there. And be careful, integral of a summation seems awful weird, but you have to remember what we're looking at here. And so we'll talk about both sides. This talks about an individual force doing work. But if I have 10 forces acting on a single object, and I add up all the different forces that were doing work on the object, I would have the net force acting on the object. So whether you find the individual amounts of work being done, or you find the work done by the net force, you could find the same thing. So I'm going to tend to focus on this today because we're going to try and take it easy on you guys. But you could consider finding a net force first and then finding out the work it does. Now, what does this mean? What do you think? Go ahead. It's a small change in displacement, right. So if I apply a force over a small change in displacement, and I'm actually going to say small change in position because displacement is change in position. So ds just represents a small change in position. So if a force applied to an object causes a small change in position. Now the dot product is here because the only part of that force that can actually do work is the part of that force that is in the direction of the displacement. So the dot product helps align our force and deal with the fact that it has to be only force in the direction of the displacement. That's what the dot product is there for. The summation is to indicate that there might be some larger displacement. Like maybe we're going from one place to another, say position initial to position final. Now, if your force is a constant over that entire displacement, you may not have to do the sum. But if your force is changing over that entire displacement, then you have to break up your force into small amounts and evaluate the small amount of work done for every little increment as you go from the first position to the last position. So the reason why it's written as an integral is to not make any assumptions about your force. Now, if your force is constant and stays in the same direction the whole time, well, then you could pull out from your integral the force part and the information about the angle. And then just add up your displacement. Meaning if the force and the angle at which it is applied never changes, then you could come up with a simpler way of calculating the work. Of course, this sum over the displacement would just be the entire displacement. So this is why AP1 had this formulation for work last year, and why mechanics had this formulation for work last year. So if you're just pushing a cart across the room, this is probably sufficient. Because as you push the cart, you can push with a constant speed at a constant angle. You can figure out how much work was done on the cart. But if you're trying to compress a spring, with every small change in position, it got harder to push in on the spring, because springs require more force the more they're compressed. Well, then I'd have to use this, because for every small change in position, I need to change the force required to compress the spring. That would require a force that is changing over the course of my displacement. At least one thing to this, and that is I want to take a minute and talk about net work. If you remember, dealing with net work, the left side here is the sum of all the work done by every individual force on your object. So I'm going to leave that here. But the right side, those of you who are in mechanics in AP1, you're learning something. That if this force is unbalanced, okay, that's important here, unbalanced, then our net force has to equal MA. Correct? Now, let's for the time being assume that the object's mass isn't changing. That does limit some of the problems we can look at, because there's plenty of problems where the object's mass changing makes a big difference. A rocket problem is a good example of that, because the rocket's mass is changing dramatically over the course of the impulse provided by the engines. So having a constant mass problem, probably not going to help us if I want to figure out how much fuel is necessary for a rocket. Does that make sense? But for a problem like this, let's say the mass doesn't change. We just know that the object is going to be accelerating over some displacement. Let's go ahead and make the same assumptions we made before, just so that you can see this clearly, okay? Let's make first the assumption that we have a constant net force applied at a constant direction. Is that okay with you guys? That's going to allow me to write this as where theta is the angle between the acceleration and the displacement. Now, one more step further with this one, that angle's got to be 0, right? The acceleration is either going to be completely in the direction of the displacement, if we're talking about standard kinematics, or it's going to be opposed to the direction of the displacement, unless we're applying it purposely at an angle, in which case only the part of the acceleration that's causing the change in displacement is going to matter anyways. So let's just go ahead and put our acceleration in the direction of the displacement so we don't have a pesky cosine just laying around on the side for no reason. Okay? So we're putting in 0 degrees, and it's just to simplify the math. So that those of you who are here for the first time on this can kind of follow along with some implication I want to make. When I do that, I get something that looks like this, MA delta X. Is that okay? So this side network. There's a whole lot of Galilean motion equations for situations in which there's a constant acceleration. And everybody who had AP1 and had mechanics knows them. 5 motion equations, right? I'm going to identify one of them that I want to look at, because only one of them has the product of the acceleration and a displacement in it. And it looked like this. There were other ones there, but none had the product of acceleration and displacement. And our network has the product of acceleration and displacement. So I'm going to solve this for A delta X. And now through some simple substitution, I can drop this into my network relationship. All good? I'm going to expand this. Please tell me this looks familiar, at least a little bit. So just a little bit of kinematics, and there's another way we could have done this, but this one felt like the simplest one. But what this tells me is that if we have work being done by an unbalanced force, then we are changing a different property of the object than maybe we thought we were talking about. We talked about it just in the sense of velocity, but what we're actually saying is that if you have net work being done on a system, and I mean specifically work being done by an unbalanced force, then you are changing the kinetic energy of the system. This term is kinetic energy. This is called the work energy theorem. and it's a very powerful theorem in physics, but it has limited uses. We have to know when we can use it. We can use it when the net force is unbalanced. But it also tells you that if an object's kinetic energy changes, work was done. There are situations in which this is really helpful. All right, we've covered a lot of the basics of work from like first semester physics. Our definition of work is complicated, but not terribly so. Work done by a net force leads to a change in object's kinetic energy. Work done by constant forces can be often simplified by dealing with the angle at which the work is applied to the object. But this is our definition of work. It's from here where I want to build something about how electricity and work are related. So can I start from here? Excellent. Excellent. Well, if I recall, we talked about the definition of the electric field. We said the electric field is defined as force per unit charge. Now, we then spent the next 5 weeks talking about different ways we could calculate this or find the shape of an electric field around objects, right? So we have really good knowledge about coming up with an expression for the way the electric field looks. Or at least you watched a lot of stuff about how we have some things out there that could help us figure out the electric field around objects, right? So Coulomb's law, summation of a distributed set of charged particles, or Gauss's law in situations in which we have some kind of symmetry that allows us to use Gauss's law to find the electric field. But the reverse of that, too, is to say that if I want to know the force in a charged particle, all I need to know is what the electric field is. And I can come up with an expression for the force in a charged particle. Just simple substitution would allow me to change my definition for work to deal with the electric field. So this would be the definition of work done by an electric field on a charged particle. So if I know that there's a region of space filled with an electric field, and I drop a charged particle in that space, then the work done on that particle would be related to the charge on the particle, the electric field filling the space, and where that charged particle moves inside the region of space. So I could have a complicated electric field, but I could still calculate the work done on a particle as it moves from one place to another. Now, something you probably don't remember from last year, because it didn't seem to probably make a whole lot of sense to you, but work done by an electric field would be considered the work done by a conservative force, because the electric force is a conservative force. We defined potential energy, or changes in potential energy, as minus the work done by a conservative force. This is a definition from last year, and I don't know if you remember it or not, but we defined potential energy this way. And I'm going to do an example in a minute to remind you of this. But this is how we defined potential energy. With this definition, we could say that the change in electrical potential energy will be equal to minus the work done on a charged particle in an electric field. This is where we start today, defining how we change an object's potential energy. In order to change a charge's potential energy, we need to give it a region of space where there's an electric field and allow that electric field to do work on the particle. Now, remember, this minus sign here is going to probably come and be a bit of the bane of our existence as we work on changes in electrical potential energy. So let me remind you about where that negative sign tends to fall into place, okay? Consider this example. I want to use an example you are quite familiar with. So let's say I have a house and I have a rock, and I'm going to lift the rock and put it on the edge of the roof. And let's say the edge of the roof is, a distance d above the ground. My rock has a mass of m. Okay? All okay? Now, if I lift the rock, I could be doing work on the rock. Let's say I lift the rock at a constant velocity upwards the distance d. Let's talk about the work done by me. I am not a conservative force. I'm just some guy applying a force. I'd probably be applying a normal force to the rock. But the force I would apply, let's say, is a constant force, so that I can use F times cosine theta times delta x for my definition of work. And this is the work done by me. Okay? Go ahead.
Can you define conservative force?
In nature, we have, for us, there's 4 conservative forces, the fundamental forces of nature. There are other forces that do conserve energy, but we can start with just the 4 fundamental forces because we know by definition they conserve energy. So that'd be gravity, the electromagnetic force. I'll say the words weak nuclear, but who knows what that means. And the strong nuclear force. These are the fundamental interactions we know by definition they conserve energy. There are some other forces that conserve energy too, but let's just focus on those. Because the only one that's really going to come up in this class is electromagnetic. Now, for me to lift a rock, I have to apply a force that's at least as strong as the weight of at least as big as the weight of the rock. And if you don't remember weight from last year, you calculate weight as just mg. Right? So let's say that there's the force by me. I'm pushing up on the rock, and the rock is going up, so that would mean cosine 0 degrees. And my delta x would be, d. All good? So the work I do is F of me times d. This is the work done by me. I know, however, that if I push the rock up at a constant speed, that the net force was 0, correct? There's only 2 forces acting on the rock, me and gravity. So this has to be equal to the force done by me. So I could write this as mg times d, the work done by me. Correct? I did positive work on the rock. Well, we'll have to pick this up tomorrow.